Welcome to part 3 of topic 4 of the IB Computer Science curriculum. In this video, I'm specifically going to focus on searching and sorting. And for each searching algorithm, as well as sorting algorithm, I'm going to give an explanation, code, and maybe take a look at some sample IB questions. Furthermore, I'm going to compare both of the searching algorithms rather, and both of the sorting algorithms. This will be followed by a quick channel update. Let's get started. Before we actually get into linear search, our first search algorithm, I want to talk about what exactly you need to know for the IB exam. So one thing you do need to know is you do need to know how to explain how all 4 algorithms work. So how linear and binary search work, and how bubble sort and selection sort work. And perhaps the most common question or type of question that's linked to this topic is writing a text-based description of how any one of these algorithms work. Now next, there's a lot of confusion as to whether you actually need to be able to write code in pseudocode for these algorithms. And what I will say is that at some point I have seen questions involving actually writing IB pseudocode for these algorithms on past paper 1s, for both SL and HL. However, I would say that it's extremely rare on the SL exam, and if it does exist, it's more common on the HL exam. So if you don't have the time to learn how to code all 4 of these exams, I would at least focus on being able to code a linear search, which is by far the most common sorting and searching based code question on the exam. However, if you are doing HL, I would recommend that you know how to code all of these algorithms. Now next, you need to know about when you can use binary search. Hint, you can only use it on sorted arrays, and we'll go into that more in detail. And finally, you need to be able to compare the linear and binary search and bubble sort and selection sort, knowing some of the similarities and differences between both of them. And again, we'll also go through all of this in this video. Anyways, let's get started. Now, whenever we're searching for something, what that basically means is that we're going to look into an array or a list of numbers to find a particular value. And we're looking for either the index of that particular value, or we want to go through and then find that value and complete some operation on it. But a search means we just want to find something. And generally in the IB exam, we're going to be looking at an array. So a linear search is the simplest type of the 2 searches, and I'll just illustrate that by going through an example. Let's say that we want to find some target value, 51. The term target value just refers to what we're looking for. In linear search, we're literally going to go through the array one by one to find our target value. So we'll start at 31, check, is 51 equal to 31? No, keep going. Is 54 equal to 31? No, keep going. And we just keep going to each subsequent element in the array until we find what we want. Here we see that this is equal to the target value, and so we're basically done. And what we'd probably end up doing, or we'd probably end up outputting in any code, would be the index where we found a match, which in this case would just be 4. And that's a linear search. We're literally just going to go through every element one by one from beginning to end until we find what we're looking for. Now, when we're actually running code for this, we may stop when we find a match, we may not stop. It depends, and honestly, the result is going to be the same. It doesn't really matter. So now that we've seen how a linear search works, let's go ahead and see how we can actually code this using IB pseudocode. Now, we've already entered nums in as pseudocode, and what we're going to do is we're going to set our target equal to 51, like in our previous example. We're also going to create something called a flag, which you may or may not have come across, and that's just going to be a Boolean variable that allows us to keep track of whether we've actually found the target in the array or not. So we're going to say found equals false, and then we can say loop I from 0 to nums.length -1, and we can say if nums I is equal to target. So going through the entirety of the array from 0 to the last index, if nums equals target, then, actually I guess it's got to be 1 equals in pseudocode. Output, we can just output a message, target found at I, and then we can change our flag. We can say found equals false. Then we can end that if statement. We can do end if and end loop. Then we can also, well, what we also want to do is create an if statement to handle what happens if we never found the target value in the array. So you can say if found equals false, then just output a message and just say target not found in array, and end if. And that's about it. So as you can see, the linear search is fairly straightforward. Just go through the array, check whether each of the elements is equal to the target, and if so, actually this is got to be found. This is actually got to be true. If so, output a message at the index where it was found, and then change found to true. And if not, then we'll output a message if we go through the entirety of the array and found is never changed, if found remains false. Okay, now let's talk about the binary search. The objective of the binary search is the same, which is to find some target value. However, there are two important differences. First, we can only do a binary search on an array that has been sorted, either in ascending or descending order. For example, this array nums is sorted in ascending order, with the smallest number, 23, being at index 0, and the largest number, 67, being the last element in the array at index 7. So, I mean, this has 8 elements, so first index 0, last index is 7. Now, the second difference is just the way in which we approach the searching. Basically, we split the array in half each time until we find our target element. So let's say that in this array, we want to use a binary search to check if 61 is in the array, and if so, at what index. So let's say that the index is 61. The first thing we need to do is we need to find an element at the center of the array. Now there are two candidates for this. It could either be 35 or 51. It doesn't really matter which one it is, but we'll just start with 35. Now we're going to basically consider two things here. First, we're going to check whether the target is equal to 35. So is 61 equal to 35? It's obviously not. So what we're going to do is we're going to check whether 61 is greater than or less than 35. Now 61 is greater than 35. So we're going to go ahead and focus on the portion of the array that is greater than 35. So that's this portion right here. Then we're going to repeat the same process. We're going to choose an element at the center of the array. Again, there's two candidates here. It could be either 54 or 61. For argument's sake, let's just choose 54. Now, we're going to check, is 54 equal to 61? It's not. But is 61 greater than or less than 54? 61 is greater than 54. So now we're going to focus on on the portion of the array that's greater than 54, which is this portion right here. Now right here we have two possibilities, 61 or 67. We're generally going to choose the lower of the two, and I'll go into why that is in a second. So we end up at 61. We check, is 61 equal to 54? It is. Or 61 is equal to 61. So we find a match, and we can output the index. Now, as to why we chose the lower element here, I mean, honestly, it doesn't really matter. We would have ended up finding 61 or finding the index of 61 at the end. But generally, when we start out with this binary search, and we're looking at the first index and the last index, the way we can find the element in the middle of those is we can add them up and divide them by 2. Or divide them by 2 using the div operator. So we could do 7 plus 0, div 2, which is going to equal 3. So we would start at index 3 right here. Then when we move up to the portion that's greater than 35, we were at index 4 and then index 7. Those were like the upper and lower bounds, or the lower and upper bounds of that new portion of the array we were looking at. So in that case, we could just do 4 plus 7, div 2, and then we would end up, so it's going to be 11 divided by our div 2, and then we just end up with index 5, which was this one right here. And then we moved to the next portion of the array, which was like the purple portion, and that was at index 6 and index 7. And then we would do we do 6 plus 7, div2, which is just 13 div2, which is going to equal 6. So that means that we would go to this element right here. So basically what I wanted to do in this example is illustrate just how we can do this process just by eyeballing it, and then also explain the math behind it, because that'll be useful when we get into actually coding. Now, let's go ahead and look at another example. So right here, there are two important differences between this example and the previous example. First, we're going to have a different target. We're going to say our target equals 23. And then this array also has an odd number of elements instead of an even number of elements. So the previous array had 8 elements, this one has 7 elements. So our first element is going to be at 0, and our second element is going to be at 6. So I'm just going to go through the process without using mathematics. What's at the middle? Pretty clear, 35 is at the middle. Now, compared to 35, so 23 is not equal to 35. 23 is actually just less than 35. So we're going to look at these at this portion of the array, and we'll go to the middle. 29. 29 is, so 23 is actually less than 29. 23 is less than 29. So then we're going to go to our new portion right here, and there's only one element, and that's equal to 23, so we have a match. Now, whenever we go through this binary search process, we are going to get to a point where there is only one element, either one or two elements left in our set. And basically, if you get to a point where, so I mean right here, we got to the point where there were only 2 elements left and we found a match, so we just stopped right here. However, if you get to the point where we only have like one element left we're looking at, and it's not equal to the target, then we just know that that value is not in the binary search. So we can have situations where an element is not in the array that we're, the element is not in the array that we're analyzing. For some reason I said that is not equal to the binary search. I meant, or is not in the binary search, I mean that the target is not in the array that we were performing the binary search on. Now let's look at a slightly longer example. And I'm going to look at this just by doing the binary search, and then I'm also going to do the math. So, all right, right here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 elements, I guess. So it means this is going to be 0, and this is going to be, I'm just going to make that blue. This is going to be 0, this is going to be 10. So let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Always helps to make sure. Now let's say that our target is 29, okay? So I just want to look at what's in the middle. So I think that's 61, just because we have 5 elements on one side and 5 elements on the other. So that's going to be at index, I guess that's index 5. Again, we could have also found that with 10 plus 0, div 2. So 10 div 2 equals 5. So now I'm going to compare 29 to 61. 29 is obviously less than 61. So we're going to focus on this part right here and look for what's in the middle. And that's going to be 31. Again, we could have found that by doing, like, what is it, 4 plus 0? Because it's 4. 4 plus 0, div 2, which is just going to equal 2. This is index 2. Now 29 is less than 31. So we're going to focus on the portion less than 31, which is this right here. Now we can choose either of these two elements. Again, we're probably going to choose a lower, because we're going to have 0 plus 1 div 2, which is just going to be equal to, that's probably going to be equal to 0. So we'll be right here at 23. And then we'll check, is 29 less than or equal to, or less than or greater than 23? And 29 is greater. So that was our middle, but now we're going to focus on a portion right here, which only has one element. And we can just check, is 29 greater than or equal to 23, or is it equal to, sorry, is 29 greater than or less than 29, or is it just equal to 29? And it's equal to 29. So that means we're good. We have our match at index 1. So now that we've seen how the binary search works, and we've also seen the math behind the binary search, let's see how we could approach this from the standpoint of writing code. because there may arise a circumstance, there have been past papers where you've actually had to code a binary search, or at the very least, describe a binary search with an amount of detail that basically requires that you know how to code it anyways. Okay, so let's see how we can approach this process programmatically, so we can understand like how we would actually work through a binary search using code before writing the code itself. Now, the first thing we would want to do is create a variable called target. And this would just be to hold the value that we're looking for, or the value that we're searching for using the binary search method. Next, we would want to create another variable called low that's going to be at the beginning of the array, and a variable high that's going to be at the end of the array. And then we want to create a variable mid. Now, mid is going to be low, so we'll say mid equals low plus high div2, following the mathematical formula we went over in the previous examples. So at least when we start out, mid is going to be assigned to 35, because high is at 6 and low is at 0, and that would make mid 3. Now this is just where we're starting out, but what we want to do next is we want to compare target to mid. So we're going to say if target is, so we're going to compare we're going to say if target is less than mid, then we're going to move high to mid minus 1. So that means that now high is going to be equal to mid minus 1. So this will be our new high. On the other hand, if target is greater than mid, so we have a situation where target is actually greater than mid, that means that we're going to be focused on this portion, whereas we were focused on this portion when the target was less than mid. So what we're going to do now is we're going to say that low is going to be equal to mid plus 1. So we're basically using a low and high to define the portions of the array that we're going to analyze in each step. Of course, before we to make any of these changes for whether target is less than mid or greater than mid, we would obviously check whether the target is equal to mid. In that case, if the target is equal to mid, then we would just return mid, right? Then that means that our answer is just going to be mid. Our index is just going to be whatever is at mid. That's kind of our goal. Now, once we've changed our high and our low, then we would calculate a new mid. So for example, if target is less than mid, then we calculate a new mid, and we check, we basically use the same formula we had before, which is mid equals low plus high, but actually be using the old low and the new high. So I'll just go ahead and I'll erase low. So it'd actually be the old low and the new high. So it'd be low plus high div2. And that would just make, basically in that case, then we'd have mid right here. And if the target was greater than mid, then we would have mid is going to be equal to I'll go ahead and write that here, the new low. So it'd be low plus the old high, the new low plus the old high, divided by 2, or div2. And that would give us a new mid right here. And we're basically going to keep carrying out this process until low is equal to high. So let's say that our target, for example, is 61. Actually, if our target was 61, then we'd have a mid, and we'd compare our target to mid, and target would be equal to mid, so we'd be done actually. So if target's ever equal to mid, then we would just stop our program. And if not, then we would keep continuing until the condition where low is equal to high. Because that means that we're basically going to be on a single element. It means our portion has been reduced down to a single element, which might be, for example, 67. if that was our target. So basically, we're going to be doing this whole process. So this process right here, checking whether target is less than mid, greater than mid, and equal to mid, and then subsequently changing our lows and highs, while low is less than or equal to high. Once that condition's false, then we stop moving around low, high, and mid and just doing all of this, because we've either gotten to the point where we found a match, or we've gotten to the point where we've settled on one last element, and maybe we haven't found something. We've either found something or we haven't by the time this condition ends up being false, and our loop would stop. So now, having an understanding of how a binary search would work programmatically, let's go ahead and write the code itself. Okay, so we've already gone ahead and we've created our nums array, which comes straight from our example right here. And what we want to do as well, we defined our target variable as well. And now what we want to do is define low and high, and low is going to be equal to 0, so basically the first index, and high is going to be equal to nums.length minus 1, which is going to be our last index. And then we're going to proceed to create our loop, which is going to be loop while low is less than or equal to high. Then go ahead and do whatever it is we need to do. And here we're going to start with mid being equal to low plus high, div 2. So we'll just have low plus high, div 2. And we're basically going to have another condition that's going to say that if nums mid is equal to our target, or I guess in pseudocode we're just using one equal sign, is equal to target, then go ahead and we can just output, we want to output the index at which we found it, so we can just go ahead and output mid. Now I'm also going to create a flag, so I'm going to say found equals false, and we're only going to change this if the value has actually been found in the array. So right here we can just say output mid, so just print that out, and then we can say false, or so found equals true. Now, this is something we're going to check in each iteration every time that we change low and high. But to actually make changes in low and high, we're going to have another if block. And by changes in low and high, I mean changing based on how the target compares to our mid value here, and then subsequently when we move around our mid based on what is in our array. So we've got if nums mid equals target, and we're also going to close up this if block, and then we're going to have if nums mid, or rather I would say if target is greater than nums mid, then, so this is going to be the situation where the target is somewhere in here, it's greater than the mid, then we're going to say low is going to be equal to mid plus 1, so right here, and we're going to say, well, so this is going to be if target's greater than nums mid, but we're also going to have an else block here, and the else block is going to be if target is less than nums mid, and we can do that because the case where they're equal to each other has already been taken care of. So if we get to this block and the target is not greater than nums mid, then it must be less. So here we'll say else high is going to be equal to mid minus 1, which is going to be the situation right here. Basically where the target is less than mid. So we've got that, and then we can end this if statement and we can end our loop. And now we can deal with the situation which just basically the target was never found. And we can just say, so if found equals false, I'm terrible at typing, then we can just return, or we can just output target not found. And that's basically the binary search. What I want to do now is take a look at a practice question specifically connected to binary search. Now, we're not going to look at a linear search question because frankly, all the linear search questions are basically the code that we wrote. But the most common binary search question looks like this. Outline the steps involved in performing a binary search on an array of ascending numbers, or it could be descending numbers. Probably the best answer here is in a numbered fashion. And it basically follows the algorithm that we just wrote with one exception. So right here, it says calculate mid, if array mid is the search value, and else do basically the things we talked about in the code, and repeat steps 1, 2, and 3 until found. Until found is the difference between what we wrote. Basically, we had a while loop that says continue while low is less than or equal to high. So basically, it's going to stop when that condition isn't true. So when low is neither less than or equal to, or when low is neither less than or equal to high. But here, particularly if we're looking at a problem where we're going to assume that the target value exists in the array, we can just repeat steps 1, 2, and 3, or we can just repeat our algorithm until we found the target value. And that could also go with a while condition. So we could just say loop while target is not equal to mid, or something like that, depending on the nature of the question and the array that we're working with. So I wanted to show you this question because it's a very common binary search question, but I also wanted to highlight another possibility when writing code if you have to. Beyond all of that, this is undoubtedly the best way to answer this question. 1, 2, 3, 4. Don't write a huge paragraph, make everything super clear. Now moving on, the last thing I want to look at with regards to searching is a comparison between linear search and binary search. So we can start with some pretty simple points of comparison. The first is the search direction. So linear search is sequential, meaning that we're checking an array one by one to see whether a value is there, and binary search effectively divides the arrays into half. The prerequisites to binary search are that the array must be sorted, but there are really no prerequisites to linear search. And practically, a linear search is best for small arrays or unsorted data, and the binary search is ideal for large arrays and sorted data. Now, to see why, we want to take a look at the number of comparisons that both will make in the best and worst case scenario. We're going to create an array. We'll just make it ordered so we can work with both binary and linear search. Let's say 1, 2, 5, 9, 11, 13, 15, 17. So we've got 11 elements in this particular, 8 elements in this array. Now the best case scenario for a linear search is one comparison. By comparison, I'm talking about checking whether the target is less than, greater than, or equal to a specific value. Now this is important because every comparison takes up a certain amount of memory and processing power. Now the best case scenario for a linear search is that the value we're looking for is at the 0 index. So we only need to make one comparison, and then we found the index of our target value. Now the best case scenario for a binary search is when our target value is in the middle. So for example, if our target value is 9 in this array, that would be the best case scenario for the binary search because that would be the first value we look at, and we'd only need to make one comparison. Now the worst case scenario is where in a linear search, we have a value all the way at the end of the array right here, because that means that we would have need to check all of the values in the array, including the last one. And so we'd have n comparisons where n is the length of the array. So that means that in this particular case, because we have 8 elements, we'd have to make 8 comparisons, and that would be a worst case scenario. However, if we go back to example of our binary search, our worst case scenario looks a little different. It's going to be log 2 of n, where n is the size of our array. So that means to be log 2 8, which just equals 3, or 3 comparisons. Now let's say that we're looking for a value like 2. First, we would start the mid. We would see that 2 is less than 9. So then we would actually end up at, I guess we'd end up at the mid, which would not be the worst case scenario. Probably a better example might actually be even 1, if we were looking for 1. We'd end up at the mid, and then we'd look right here, and then our next value would be right here, and then finally we'd end up at 1. And that's basically a worst case scenario for an array with 8 elements, and it's less than, and the worst case scenario is actually better with a binary search than for linear search. Now there's one caveat to that if we're talking about efficiency. Yes, there are fewer comparisons in a binary search, but we also do need to sort an array. We need to make sure that we have a sorted array, and sorting by itself takes up a bunch of memory and processing power. So unless the array we're looking at is already sorted, binary search may not necessarily be more efficient than a linear search, but we definitely do need to make, so if we have a scenario where we do have a sorted array, then a binary search is definitely going to be more efficient than a linear search, all things being equal. Anyways, that's linear search versus binary search. Let's move on to sorting. So the bubble sort is going to be the first sorting algorithm that we're going to look at. Now, in general, sorting algorithms are meant to take an array and sort it in ascending or descending order. So let's see how the bubble sort can do that. So the first thing we're going to do is we're going to start with the array, and we're going to start with 31 and 54. So 31 is less than 54, so we're not really going to do anything. We're basically going to compare each element to the element after it, and if the element after it is less than it is, then we're going to swap them. Otherwise, we're not. So you've got 31 and 54. Now we're going to compare 54 and 67, but 54 is less than 67, so we're still good. Now we're going to compare 67 with 29, and 29 is less than 67, so we're actually going to go ahead and we're going to swap them. So we'll erase this, and then we'll have 29 and 67. Now we're at index 3. So after 67 will be 51. And 51 is actually less than 67. So basically 67 moved over here. So 51 is less than 67. So we're actually going to swap those. So this will become 51, and then we'll have 67. So now 67 is actually at index 4. So now we're going to compare 67 to the next number, which is 61, right here. And 61 is less than 67, so we're going to go ahead and we're going to swap them. And so we'll have 61 and 67. Now the next element is going to be 23, because we swapped 61 and 67. So 23 is less than 67, so we're going to swap them again. So we're going to have 23 and then 67. And finally, we just have 35 left, and 35 is still less than 67. So we're going to swap those, and we're going to have 35 and 61. Sorry, 67. So as you can see, higher values bubble to the end of the array. Now, one thing you might notice is that this array is still not sorted. We need to have multiple passes to go through the array until we can actually sort it. And we tend to run this array for the number of elements there are in the array itself. So now that we've done that, let's go ahead and let's see again what we're going to do. So we've got 31 and 54, all's good, but 29 is less than 54, so we need to swap those. So we're going to have 31, 29, and 54. And now 54 is greater than 51, so we're going to have 51 and 54. And 61 is actually greater than 54, so we'll just stick right there. But 23 is less than 61, so we're going to have to swap those. So we're going to have 23 and 61. And now we've got 61 being less than 35, or 61 being greater than 35. So we're going to swap those as well. So we're going to have 35, 61, and then 67. And so you can kind of see how things are slowly starting to fall in order. But let's keep going. So we've got 31 and 29. 29 is less than 31, so we're going to swap those. So we've got 29 and 31. And 31 is less than 51, so we're not going to do anything. 51 is less than 54, so we're not going to do anything. 54 is less than, or is greater than 23, so we are going to swap them. So we're going to have 23 and 54. And 54 is greater than 35, so we're going to have to swap those as well. So we're going to have 35 and 54, and then 61 and 67, and there's no swapping there. But let's keep going. 29 and 31 are good. 31 and 51 are good. But 51 is greater than 23, so we need to swap those. So 23, and then 51, and then 35. But actually 35 is less than 51, so we need to swap those. 51. And then everything else is pretty much sorted. And so we're just going to repeat the process again. 29 and 31 are good, but 23 is less than 31. 31 is greater than 23. So we're going to have 29, 23, 31, and 35. And we're pretty much not going to swap anything else because the rest of the array is in order. But we're not done yet. So we've got 29 and 23, which we can swap. So we're going to end up with 23, 29, 31, 35, 51, 54, 61, and 67. And that's basically how a binary search works. Each time we're going through, we're comparing one number to the next. And if the next number is less than our current number, then we're going to swap them. Now this is going to produce an ascending order. If we wanted a descending order, we would just do the reverse. So we'd compare the number next to it, and if the number next to it is greater than the current number, then we would swap those rather than less than. That's basically how a bubble sort works. So now what I want to do is focus on how we can take a bubble sort and write code to execute this algorithm. So if you look back at the process that we just went over, basically we had higher values bubble to the top. By the top, I mean the end of the array. So first we had 67 right here, and then 61, and then 54, and then 51, and then 35, and then 31. So basically it took us 1, 2, 3, 4, 5, 6 times to get this done. And in this array, there are, let's see, what is that? There are 8 elements. So we kind of got lucky in the fact that these last two arrays ended up already, or these last two values ended up already being in ascending order. But that's not a guarantee. So when we are doing sorting, we're basically going to have to do this the number of times. We basically have to do this 8 times, or the number of times that's equivalent to the number of elements we have in an array. So if we think about a loop, we'd have to go from 0 to n minus 1 times. Right, so from the first index until the last index. So basically, again, in this situation, we'd be going from here to the end, and we'd be going through this process the number of times equivalent to the number of elements in an array. So 0 to n minus 1. But each time, we're going to kind of do something different, right? So if we go back to this process right here, so the first time around, we traverse the array from here to here, okay? I mean, that's all that was necessary. We didn't have to go through the end because we were just going to swap values with whatever was at the end. So we had to check what was at the end, but we didn't actually have to go to the end, go to the last index. Then we just had to go from here to here. And then from here to here, and here to here, and here to here, and so forth. Okay, so basically to recap, we're going through this array n minus 1 times, okay? Right here, we didn't really go through n minus 1 times, but in general, that's what it would take to get to the end of the bubble sort. Now each time we're going to a different index. So the portion of the array that we're covering each time gets smaller and smaller. So here we went from 0 to index 6, because there's 8 elements. 0 to index 5, 0 to index 4, 0 to index 3, 0 to index 2, 0 to 1, and then eventually we just would have had 0, right? So we're covering an amount or a portion of the array that's getting reduced by one element each time. And if we turn this into a formula, we can say that we're going to go from 0 right here, 0 to n minus 1, minus 1, right? And then 0 to n minus 1, minus 2. And then n minus 1, minus 3, n minus 1, minus 4, n minus 1, minus 5, n minus 1, minus 6. And we're actually, I mean, there's no point in getting to 0, so we're basically going to do this, right? And I want you guys to keep this pattern in mind, because now when we go to write code, we're going to take this and apply it in a loop structure. Now, basically each time we go through the loop, so each time we go from value to value, which is this one right here, like the red, so this one's controlling the number of times that we go through the array, and this green is controlling each element that we access whenever we go through the array itself. So that's controlling this movement from 31 to 54, 29 to 51, 61, 23, etc. That's what we're talking about with this process right here. And each time we do that, we're going to have some code to swap the element with the one next to it if the relevant conditions apply. So if it's less than or greater than, depending on whether it's ascending or descending. So now kind of having some understanding of how the bubble sort works in a programmatic sense, let's go ahead and actually write the code. Okay, so we've already filled in our array right here from our example. Now, the first thing that I want to do is I want to create a loop for basically this process in which we are iterating. So basically to control the process in which we're going from 0. So basically from this array all the way down to this array. So the process that controls how many times we're actually going to go through the array. And what we're going to do for that is we're just going to say loop I from 0 to n minus 1 to n minus 1. And n is going to be equal to nums. We're going to define that nums.length nums.length. So this first loop is going to, actually I need to say loop I, yeah, that's actually good. This first loop is going to be corresponding to the red. It's going to control the number of times we're actually going to go through the array. And then inside we're going to have another loop for for basically each time. So basically for every time that we pass through the array, we're going to be passing through a different component, and that's marked by the green, which we just went over when we explained our algorithm. So that corresponds to this right here. So basically what we're going to have is we're going to say loop j from 0 to n minus 1 minus I. And that I is representing this value right here. So that j is basically going to allow us to iterate within the component that does not include the maximum, or the maximums that we've calculated and that are circled in red. So now that we've written our two loops, what we're going to do here is we're actually going to do the swapping. So remember, when we want an array that's in ascending order, we're going to take the current element, and if it's greater than the element next to it, then we're going to swap it with that one. And we're going to keep repeating that process throughout the portion that doesn't include the current maximum or maximums. So for example, as j is going through, each time we're going to check whether the current element is greater than the element next to it, and if it is, we're going to swap them. So to illustrate that process, we can say if nums of j is greater than nums of j plus 1, so the element just above it, then temp is going to be equal to nums j, the lower number. Nums j is going to be equal to nums nums j is going to be the higher number. Nums j is going to be equal to j plus 1, which is a lower number. And then we're going to have nums j plus 1 is equal to temp. And this is going to allow us to swap those two values as part of the swapping process that j controls. So then we can just do end if and end loop for the first loop, and then end loop for the second outside loop. And that about covers it for the bubble sort. Now that we've had a chance to look at the bubble sort, let's get started with the selection sort. So what we're going to do first is, well, we want to sort this array in ascending order. So what I basically want to do is I'm going to start by finding the minimum value in this whole array. Now it looks like the minimum value in this whole array is 23. So I'm going to swap that with the first element, with the element at index 0. I'm going to end up with 23, 54, 67, 29, 51, 61, and 31, because 31 was at index 0, and then 35. So that was index 0. Now what I'm going to do is I'm going to look for the minimum between index 1 and the end of the array. So if you look, we have 23, and then if you look at the minimum, it looks like the minimum value from index 1, so from index 1 until the end of the array, is going to be 29. So we're going to swap 29 with index 1, and we're going to have 29, 67, 54, 51, 61, 31, and then 35. And now we're going to go to index 2. So from index 2 until the end, we're going to look for the minimum. So we're going to end up with 23, 29, and then I guess the minimum here is 31. So we're going to have 31, 54, 51, 61, 67, and then 35. Now next, we're going to keep going. So index 3 until the end, and we end up with 23, 29, 31, and then the minimum from 54 to 35 is going to be 35, 51, 61, 67, and then 54. Next, we'll look from 51 to 54. We've got 23, 29, 31, 35. Let's see what the minimum from 51 to 54 is. Actually just 51. So we can leave this in place. 51, 61, 67, 54. And that's pretty much it. Now we're going to look from here to here. And we'll end up with 23, 29, 31, 35, 51. And the minimum here is going to be 54. So 54, 67, 61. And next, we've only got two elements left. So, I mean, this is pretty much going to be the last iteration. 23, 29, 31, 35, 51, 54, 61, and then 67, and we are literally sorted. Now, one thing to pay attention to is that this section in purple is our unsorted portion, and the section outside is our sorted portion. And as we continually go through the array, the sorted portion will grow and the unsorted portion will decrease until it's only one element, at which point the entire array is sorted. Now, basically what we did each time is we looked for the minimum in the unsorted portion. And that was sufficient to get us, or that's what we needed to do to get the array in ascending order. However, if we wanted to put the array to descending order, then we would look for the maximum instead of the minimum. And in that case, the first element at index 0 would be 67, and so forth. So ascending order, we're looking for the minimum, and descending order, we're looking for the max. That's something to keep in mind when you have to write code to use the selection sort to sort an array in a particular order. which does actually come up on the IB exam. Okay, so now that we've seen how selection sort works, let's see how we can approach this programmatically. So the first thing to keep in mind is that we are essentially going to start at index 0. And then we're going to find the maximum or the minimum value from index 0 all the way until the end of the array. So we start at index 0 and then we go to the end of the array. And then the next time around, we'll start at index 1, 2, 3, 4, 5, 6, and then 7, although we don't necessarily need to go to 7. And each time from that index, we're going to find the maximum or minimum from that index until the end of the array, 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 and I guess it's just that element right there. Now to do this, we need 2 loops. First, we're going to need one loop to access every element from 0 to n minus 1, where n is equal to the length of the array is equal to the length of the array. So we're going to have one loop. We can just say loop, we could say loop I from 0 to n minus 1. And then basically every time I changes, we're going to need another loop that's going to go from I until the end of the array. And that can be represented by the purple lines that we used. So inside that, every time I changes, we need a loop that goes, so we need a loop j from I to n minus 1. So for example, when I is equal to 1, then j is going to go from, it's going to go from 1 to n minus 1. Actually, we'll use some different colors to make it really clear. So when I is equal to 1, then we're going to go from, so j is going to go from 1 to n minus 1. When I is equal to 2, then j is going to go from 2 to n minus 1. And as j is going from 1 to n minus 1, we're going to be finding the max or min through that process. So as we're looping through from 1 to n minus 1, we'll be executing operations to find the max or min. And we'll do this until essentially we get to the end of the array. So now we understand, now we have some understanding as to how we could write this code, then let's go ahead and let's actually write the entirety of the code so you can see how everything works. Okay, we've already got the nums array that we will be sorting. So if you look right here, the first loop we're going to write is going to be to control the number of passes that we need to turn the unsorted array into a completely sorted array. That's just going to be 0 to n minus 1, and that's illustrated by these red numbers that we have right here. So we're going to have a loop, we're going to define n as nums.length, and we're just going to say loop I from 0 to n minus 1. And then inside that, we're going to control the process that goes on right here, which is basically just finding the maximum or the minimum each time we pass through, and then swapping the value at the given index with whatever that maximum or minimum is. So basically the way that we could do that is we could say loop I or loop j from I to n minus 1, because we can go from our current index to the end, and we can say if array j, or if num j. So that means that this j is going to be going from here to here, and then here to here, and then here to here, and then here to here, until we get to the end. And then we can just say num j, or we need to calculate let's say we want to turn this into ascending order, which would require a minimum. We're going to create a variable right here that says min index equals I, which is basically the first element in our unsorted portion. It's going to be right here. Then we're going to say loop j from that to the end. And we're going to say if, we're calculating the minimum, right? So we're going to say if num j is less than that first element, or is less than the minimum index, that variable, then our num min index, and we can change min index to what the new minimum is. So we can say min index equals j. Again, keep in mind j is going to be the counter that allows us to go through the unsorted portion, starting at I and going to the end. That's marked by the purple arrows. And then we can say end if and end loop. So once we've actually gone through the entirety of the unsorted portion, then we can actually use our swapping logic. So we can say temp equals array I, or num I. We could also do num index if we wanted to. Well, actually, min index would have changed, so we can't do that anymore. But we can just say num I. That corresponds to the top loop. So that's going to be this value, this value, this value, this value, whatever. And then we can say num I equals num min index. So we're swapping the current minimum with that one. And then wherever min index was, we put whatever it was at num I. So we'll say num min index equals temp. And then end if. So we're going to end, actually we don't have an if statement, we're just going to say end loop right there. So all of this is happening after we've actually found the minimum in the unsorted portion, and then we're just doing the swapping process within the array. And that's how the selection sort works. So now that we've had a chance to look at both the bubble sort and selection sort in depth, let's just do a little comparison. Now, the first and obvious difference is the methodology, which we've talked quite a bit about, but also there's a different number of swaps you make. By swaps, I mean when we have something like 53, 67, 69, 71. I guess, okay, let's just make this like 51 just so it's not sorted. Swaps is when we're actually swapping elements, and partly because we do need to hold, we need to create an extra variable and hold a value in memory while we swap them. This can be memory inefficient or take up some memory space. Now, this isn't really a big problem until we get into values that consist of like millions, or get into millions, but it's still something to consider. So basically with the bubble sort, when we go through a bubble sort, every time you pass through, because our maximum values are bubbling to the top, like for example, we'd have 69 eventually ending up right here, we're making multiple swaps each time we go through for this bubbling process. But with the selection sort, we're only making one swap each time we pass through an array. That's a swap between the maximum value and the value of the current index that we're on in the sort. So in some ways, a selection sort can actually be more efficient than the bubble sort, but it really depends on the circumstances. So I would say besides the methodology, this is one big difference. Now let's take a look at some IB questions involving both the bubble sort and the selection sort. So describe how a selection sort algorithm could be used to sort the array 3 in ascending order. Here we have a paragraph that basically simulates the code that we wrote, which is why I wanted us to write the code. I'm not going to go through all of this, but I just wanted to show this to you as an example of probably one of the most common selection sort questions, although I have also seen pseudocode coding questions involving selection sort. Okay, so now this next question is a great question that speaks to our comparison between bubble sort and selection sort. Identify two differences and two similarities between a bubble sort and a selection sort when sorting an array of 10 elements. So the comparison given here is that both use nested loops, which is true, each time reducing the inner loop, which I guess if we're talking about reducing the inner loop, that means that I don't know if I necessarily agree with this one, but I guess we're decreasing the set of numbers at which we're working with each time. But then also we say that the bubble sort swaps adjacent items, and the selection sort finds the next smallest item each time it goes through the list. So those are two important differences right there. And the bubble sort can exit early if already sorted. This depends on the algorithm, but that is a possibility. So we've got these two as our similarities, and basically these two as our differences right here. Now, for some channel updates, In the short term, I have 2 videos that I'm planning on making, which are a part 2 of the SL pseudocode problem series and a part 1 of the HL pseudocode problem series. In the long term, I am thinking about making an option B video. I haven't really decided yet. Definitely going to add some more A-level videos, which probably aren't relevant to you, but it kind of tells you what I'm doing. And then I'm going to start work on a new channel, which I'm really excited about, and I will be announcing somewhere here soon. Anyways, I hope this video was of value to you. If it was, please consider liking this video and subscribing to the channel. Have a nice day.